So here's a method of sections problem. I prefer method of sections over method of joints because typically you can eliminate some of your unknown variables by making a cut through your structure. I broke it down in a 4-step process. The first one is just to determine where your desired force members are located. And then after that, you choose a place to chop and then draw a detailed free body diagram, which we have drawn here, and then solve for the variables using your summation equations. So when it comes to your desired force members, we have BE, EF, and CB is what's being asked for in our prompt here. So we look at our initial drawing, we have BE here, we have CB here, and then we have EF here. So they're all in the same general area. So that lets you know that you'll probably be able to make a clean cut across this structure. So when I choose a place to chop, it's probably just going to be right across the middle here. So I'll go ahead and make that cut. Okay. So after your cut's made, you can kind of look at both the bottom and the top of the structure to determine how do you want to draw your free body diagram. So looking at the top here, we already have these external forces, already have values. So that will automatically make me want to use the top, because if you look at the bottom, you have these supports here, and these are all unknowns. So you most likely will have to solve for these unknown variables as well on top of your three force members. So in this case, it's probably better to use the top section for your free body diagram. So if you look over here, this is the top section of the free body diagram. I just rotated it to the right for a better visual aid using these X and Y coordinates. So you can see point D is here, well, point D is up here, and then I forgot to label the 5 kilonewtons for point D, so we'll go ahead and do that real quick. So when it comes to the free body diagram of a section, you have the option to draw your forces in either compression or tension. As you can see here, I decided to draw all 3 of my forces in tension. That means the force is going away from the point. As you can see, they're all pointing towards the right. So anything past the cut, you don't need to really worry about. So make sure you get all your external forces on your free body diagram and the dimensions. And then you can kind of figure out what the best method is to begin solving for your unknowns. So as you can see here, we won't be able to solve X right off the bat because we have 3 unknowns in the X direction. However, we should be able to knock one of them out using a moment equation. So especially particularly CB, because if you do a moment around point E, that would then eliminate these 2 unknown variables. So after that, you'll most likely be able to solve for the Y direction because you only have one variable going in the Y direction, which is EB, unknown variable, and then you have a bunch of givens in the Y direction. So you should be able to solve for that. And then you should be able to solve for the last one, EF, by doing summation of forces in the X direction, because you'll have CB, you'll have EB solved, and then you'll have this 5 kilonewtons given here. So let's go ahead and start doing that. So, like we talked about, taking the moment around the point E will eliminate a couple of variables and allow us to solve for CB. Now, with these method of section problems, it can be a little challenging to figure out which direction each force is making the entire member rotate. So I'm going to go ahead and predict the standard counterclockwise rotation. And then we're going to find the moment around point E. Alright, so the first one is our initial variable CB. So CB is going towards the right. So when it's going to be pulling on this object here. So it's almost going to be like pulling it this direction, which would cause this to rotate in the counterclockwise direction. So that means CB will be a positive value, and then it's perpendicular with point E here at a distance of 4 meters. So go ahead and put a positive CB times 4. Now let's take a look at the rest of this free body diagram. So this 5 kilonewtons is also going to be limited at point E since it's going into it. This point C, 10 kilonewtons, is also directly in line with point E, so you don't have to worry about that either. The only other external force is at point D, which is 5 kilonewtons going up, and that's at a perpendicular distance of 4 meters. So when it's pushing up this way, it's going to make it rotate around point E in a clockwise direction. So that's going to give us a negative value. So we'll go ahead and put minus 5 times that distance of 4 meters. It's going to be equal to 0. And then CB is going to be equal to 5 kilonewtons. Now, since it's a positive value, we predicted right that we have this going into we have it drawn as a tension, turned out to be a positive value, so CB is in tension. Now if that value was a negative, then it would be compression. So for the next step, we'll go ahead and want to solve for this EB variable, and we can do that by just doing the summation of forces in the y direction, because it's the only one that's unknown in the y direction and everything else is known. So we'll go ahead and get this out of the way. So we'll go ahead and do a positive direction. Now for forces in an angle, I like to use the triangle method here, which is using the base and the height that's given your dimensions and then finding the hypotenuse. Since we have 4 and 4, you can just divide that by 2. So that'll give you a triangle of 2, 2 with a hypotenuse of square root of 8. Now, since we're going into the y direction, this EB is going down, which makes it a negative value. So I use this y value here on my triangle and then divide that by the hypotenuse. So I have a negative 2 over radical 8 times EB. And that accounts for our angle here. Now, looking at the rest of this free body diagram, we have only 2 values in the y direction, this positive 5 kilonewtons and this positive 10 kilonewtons. So we'll go ahead and write those. And that gives us a value, so EB, after we isolate and then solve for EB, a positive 21.2 kilonewtons. Once again, since it's positive, we guessed right, it's in tension. Now for the x direction. We have all the values that we need. We have CB, EB, and now we just need to solve for EF here. And we can do that by the summation of forces in the x direction. So we just have to make sure we count for this 5 kilonewtons, EB, and then don't forget the CB as well up here. So positive going to the right. Summation of forces in the x direction. We'll start with our unknown variable, which is EF. Then we'll add this 5 kilonewtons here, which is 5. And then we'll add CB, which is also 5 kilonewtons, plus 5. And then once again, we have to take into account the angle of EB. So the x value of this triangle is also 2, but EB is going into the positive x direction, left to right. So we'll go ahead and add a positive 2 over radical 8. times 21.2. That's going to be equal to 0. We isolate everything to one side, and that gives us a negative value. EF is equal to negative 25 kilonewtons. Now that we know that this is negative, we can assume, or we know that we predicted wrong here, that it is not in tension, it's going to be in compression going the other way. So we'll go ahead and write EF is equal to 25 kilonewtons when it's in compression. So that's it. Big things to take away here is just look over your initial drawing and determine where all the force members, the unknown force members that you're trying to calculate for. And then once you kind of figure that out, you can go ahead and determine where you want to make your cut. And just remember, when you make a cut, you can cut no more than 3 force members. And then after you make that cut, decide which half will be better to use. Try and find the one that requires less solving for unknowns. So like what we had here, everything on the top was already solved for. So you don't have to worry about anything on the bottom half. And then just make a nice clear free body diagram. When in doubt, draw everything in tension. And then if you get a negative value, then you know it's in compression. But other than that, that's all I got.